Start. So we are discussing the evolution of a device which can give us amplification as we desire. But some feedback that I got from the class was probably it was getting too detailed or too involved in the device physics of it, which I agree. But I mean, in case you haven't got anything out of the last two classes, it's also okay. You don't affect the rest of the course. The reason I wanted to give you the how the working of at least the intuition behind working of a device is, I don't want to give you a current voltage equation of some device which you haven't seen before. So that doesn't give the flavor of that essentially loses a continuity, right? So even though you don't understand all the nitty-gritties of the device physics, that's okay. At least you will know the some key takeaways which will help you to build up on the circuits later on, right? So that's the whole intention behind the last couple of lectures. We'll spend half of this lecture also going in that same vein. But I mean, at the end of another 15-20 minutes, I will quickly recap of what are the salient points that you might want to remember, and the rest you can forget if you will, which will help us in the days going ahead. Okay. So if you recall, we were discussing a semiconductor device, and if we draw a cross section of the semiconductor device as we had been doing earlier, this is what we were at. So this was the N-type semiconductor. We put a metal somewhere here, and then we said that if we have a battery between, let's say, so we understand you cannot put a battery on, you cannot put a contact on the other side, but just for the ease of drawing, I put it like that. And then we also say that here you have a, let's say, P plus, make some P plus contacts. It's like almost like a well or a tub where you have generated a island of holes, kind of, right? And then we further say that all these PN junctions, now this is a PN junction, this is a PN junction. So all these PN junctions, we must ensure that they are reverse biased, because at the end of the day, we want the channel to be formed here. We want the carrier transport, which in other words, we want the whole transport to happen within the within that shaded region. We don't want the holes to escape through the forward bias PN junction, which essentially means that we have to ensure the batteries that we apply are in such a way that they are all reverse biased, right? So let's take some example. Let's say this battery is 2 volts. Okay. Yeah, so let's say this, okay, fine, 2 volt is fine. Let's assume this battery is 2 volt. And if I have to ensure that, let's say this PN junction is reverse biased, right? We need a reference. Without any reference, it becomes difficult to intuit. I mean, if I'm talking about one particular node voltage, it doesn't make sense. So let's assume this is the ground. Okay. So if that is the ground, then we make a further approximation that anywhere you find N, which is connected to this terminal, is a short, which essentially what I'm essentially getting at here is that let's assume that the voltage over here and the voltage over here are identical. Right? That's an approximation. That's not a very, I mean, that cannot be true, because ultimately you will have some resistance, right? You will have some resistance here. But let's ignore that resistance, assuming that N-type silicon is almost like a metal, right? So, so if that is the case, now can you comment on what is the voltage that I would need on this P-type silicon or P-type doping in order to ensure that question? Okay, can you comment on what is there a limit on the voltage that you would want on the P plus tub or P plus island in order to ensure that the PN junction is reverse biased? Less than 2, right? It cannot be more than 2. In fact, as you can see, regardless of, I mean, whether I am talking about the P plus on the top or P plus here, both the voltages have to be less than 2 volts, right? So essentially, this is what we call body, right? Body or substrate or I mean, let's stick to those two terminologies, the body or the substrate. In circuit design, mostly we refer to the bulk as the body. So we'll refer to it as body mostly. So the natural thing that comes, the natural conclusion for a circuit designer, because a circuit designer is dealing with voltages, kind of, right, at this stage. So natural conclusion is the body of this device has to be at the highest possible voltage that is available to you, because even inadvertently, you don't want to make that PN junction forward biased, right? It's quite possible that under certain circuit condition, one of these voltages rise above body voltages, then you are dead, or the device is dead, right? So you don't want to do that. So it is almost always advisable to ensure that the body for this type of device is always at the highest possible voltage, which means essentially it's almost always a battery voltage. Whatever is the battery voltage, you connect it to the maximum possible voltage, connected to that voltage. Okay. So now, so let's assume that is done. I mean, instead of assuming, we can simply say that this is the, let's say, the battery voltage, which means that this voltage, let's say, the voltage on the top, let's say, is 1.5 volt, which is less than the battery voltage. By the way, even if I keep it at 2 volt, will it be a problem? It will not be a problem. The PN junction is still not forward biased. It will not conduct. So I can as well keep it at 2 volts. Fine. So if I draw the analogy between flow of water from top to bottom and try to relate to this structure, so essentially what we are getting at the fact that you have holes here, and if you have sufficient electric field in this direction, you will have holes here also, right? Because all the electrons have been pushed away into the bulk, right? And you have only the mobile holes and the ionized positive impurities are present in that green zone. So essentially now we have a continuity of holes between this region and the channel. Okay. So now if I apply an electric field, from top to bottom, then it is expected that the holes will flow from the tub on the top to the tub on the bottom, and the channel this channel is going to control whether the holes can flow or not, depending, because essentially this electric field, which is forming inside that dielectric, right, which is air in this case, the electric field that is getting formed in the dielectric is controlling the concentration of holes in the channel. It's like the valve of the tap. You don't want the holes to be formed. You don't want the water to flow. You switch the tap off so that the pipe becomes thinner and thinner, which means you don't have any water flow. In this case, you don't want the mobile holes to be formed. In that case, all you have to do is to ensure that this electric field goes off. How do you ensure the electric field goes off? Right? So you increase, let's say I increase this voltage to 2 volt. Right? Then naturally the electric field vanishes. Right? Because now this battery essentially 0 volt battery. You don't have any channel. Okay. So now that naturally, from this you can readily see that it's kind of an electronic tap, but the third terminal is this guy. Okay. Okay. So now if I want to generate an electric field from top to bottom, all I need to do is connect another battery here. And let's say I give it 1 volt. Right. So naturally you see there will be an electric field, and the holes move in the direction of the electric field. If the holes move in the direction of electric field, I can get a current. Again, this current will now be also dependent upon the holes in the channel, and the holes in the channel are being controlled by a third terminal. Okay, so that's essentially is the working of these type of devices, right? So as it turns out, there is the name for this device is called overall this device is called a MOSFET, right? So the reason it's called a MOSFET is, you see the structure you have here is metal, This is metal or M, right? So metal is ticked off. What is O? O stands for oxide. Now, why do you see the oxide? So as you should recall, this region here is a dielectric, right? You cannot have things hanging. You have to put something there. So the most reliable dielectric in terms of both its longevity, electrical and mechanical properties on a piece of silicon is silicon dioxide, right? So this guy here is not a vacuum. You have a dielectric here, and this dielectric is often called the oxide. Depending upon what type of technology you are using, that type of oxide can change, but in general, it's an oxide. So this O stands for oxide, right? So this is metal, this is oxide. This, where I have called it N type, essentially N or P doesn't matter. This is a semiconductor, right? So this stands for metal oxide semiconductor. Now, what is FET? FET means field effect transistor, right? So now what I mean by that? Field effect transistor. So as you can see that the motion of the electrons or motion of the holes in this case even the availability of holes in this case is dependent upon whether the electric field is available or not in this direction, right? So essentially that electric field is affecting the carriers, the generation of the carriers, hence the term field effect. And this entire structure is called a transistor. Now, you will soon understand why the terminology transistor came into being in another 15-20 minutes. But essentially, this is the name of the device. It's called a MOSFET in abbreviation. Now, as you can see, one might argue that we started off this entire argument with assuming this substrate is N-type, right? We started off the entire argument assuming the substrate was N-type. We can start off the entire argument again, restart by assuming the substrate is P-type. Possible. So if the substrate is P-type, what natural changes would you see? Not only the battery voltage has changed, the P plus doping will now have to be N plus doping. Because again, that will become, using the same argument, these two cannot be of the same type, right? Because you cannot form a channel then. So this P plus will be N plus. And as you rightly pointed out, the battery voltages will also have to flip, because in that case, the desired electric field would have been in this direction, right? So the battery voltages, whatever battery voltage you see, even easy to do is basically wherever you find, the way the batteries have been connected, you just flip the polarities. You are good, right? So that's all that's going to happen. There are essentially two variants then. So this variant, whatever you see right on the screen, is called an N MOSFET, because the substrate is N-type. Sorry, this is called beg your pardon, this is called a p-MOSFET, because not of the channel. The type of MOSFET is often the definition of the MOSFET or the nomenclature comes from the type of carrier that is giving rise to conduction. In this case, the carrier that is giving rise to conduction is holes, right? The stuff that is flowing through the channel is holes. So hence it's called a p-type MOSFET. If you flip everything around, the type of carrier will become electrons, and that time we call it an N-type MOSFET. Okay, so often called NMOS or a PMOS device. Okay, so we'll get to the NMOS device later on. But the reason if you pick up any book, you will see that the initial introduction to MOSFET is through an NMOS device. We'll also do NMOS device shortly, but the reason I wanted to start off with a PMOS device is because it gives you an analogy between flow of water through a reservoir, and you can control it in certain way with this. Because if you flip everything around, then naturally you see that even though the electrons will flow from top to bottom, the current will flow from bottom to top, right? So if we start off with a reverse device or the NMOS device, so that's why I didn't want to approach it through the traditional route. Okay, fine. So now we have a device. So what should I do about it, right? So we should then see that whether this is a good enough device for us or there are some issues. So now that we have a device, we cannot each time draw a device like this, right? When we want to make a circuit, we need a symbol. The symbol associated with this is the following. So now this symbol should make sense immediately. So this parallel line denotes the capacitance, right? The capacitance that helps in developing the channel. And this terminal is often called a gate, because it's essentially gating the flow of carriers, right? It's gating the flow of carriers in the channel or generation of the carrier of the channel. So this is called the gate terminal. By the way, can you comment on one peculiarity of the device, in the sense that if you just look at the device, right, no voltages, no battery connected to it, this device is a symmetric device, right? This device is a symmetric device. There is no way you can figure out which side. I mean, I take this device, flip it around, connect it like this, it is still going to work. And that's a very peculiar thing about MOSFET. It's not true for any other. I mean, it's not true in general for any semiconductor device. You cannot take a diode and flip it around and it will still work. That's not going to happen. Not even in case of BJT or any other device that you might see later on. But because of this peculiarity, sometimes a misconception comes into picture. And I'll address the misconception shortly. But before addressing that, let me give you one more piece of nomenclature, which again we'll be using. So as you see, the current flows, or the carriers flow from top to bottom, right? Since the carriers is, at least in the way I have sketched it, the carriers, the holes are flowing from top to bottom. So essentially this terminal is, that's why I often call the source. It's sourcing the carriers. And this terminal is called the drain. It's draining the carriers out, right? So essentially this becomes the source. This is abbreviated as gate, this is abbreviated as source, and this is as drain, or rather abbreviated as D. Okay. So now when you are doing circuits, you will need, this is not sufficient. You will need another indicator as to figure out which side the current flows. In this case, the current is flowing from top to bottom. So essentially, I need an arrow to indicate which side the current flows. So generally, the arrow is put on the source terminal, regardless of whether you're using a PMOS or NMOS. So arrow goes in the source terminal, right? So I have to put an arrow in the direction of the current flow in the source terminal. So this is what the device looks like. The symbol of the device looks like this. So this arrow, again, two things about the arrow: which terminal you should be putting and which direction it is pointing to. You always put the source arrow at the terminal of the source, and the direction is towards the direction of the current flow. Okay. So now the question to you is, if I give you a device like this, a symbol like this symbol is not symmetric, right? So how would you, I mean, you take a circuit or you take a device like this, or I give you a symbol like this, how would you establish which side is the source? Because the device in a way is symmetric, but the symbol is asymmetric. Yeah, it's arrow, but let's say I don't give you with the arrow. How will you establish which side is the source then? Pardon? No, I can flip it around, and it's not like, I mean, when I use it in a circuit, right, you can draw it in any ways, right? I can draw it like this, something connected here, something connected here. Now it's a part of a circuit, right? You can have a network. You can as well have something connected here, something connected here, and so on. So you cannot differentiate whether it's pointing this way or that way. So the answer is you don't have sufficient information unless you know which side of these two terminals are at higher voltage. you need to know whether this terminal or this terminal are at higher voltage. Why do you need to know that? Because unless you know that, you don't know where from will the holes come, right? And moment you know that, moment you know what is the higher voltage terminal, you know that that terminal must be sourcing the carrier, hence that will be the source. Okay, so in isolation, it is impossible to tell or comment which side will be the source until and unless you put a battery, until and unless you define the voltages, the quiescent voltages of the terminals. Okay, that is the peculiarity of a MOSFET that you should be mindful of. Okay, sometimes in the books you will see another symbol, which is like this.
High voltage,
Yes, one with the higher voltage is the source in a p-MOSFET device. So another terminal, another symbol that you will often see is with this bubble, right? So when you see this with the bubble, you understand this is a p-MOSFET, but you still don't know which side is the source or the drain, which essentially means that it has been left to the designer, or it has been left to the person who is analyzing the circuit to figure out which is the source and the drain. Okay, but we understand this is a p-MOSFET by looking at the bubble. Okay, fine. So now that we are here, let's do one quick, let's do a sanity check, at least of some of the Y parameters, to understand whether this device is good enough for us or not, right? So let's look at the easy ones. Let's look at Y11. So let's initially assume that this is how the device is. Hold on 1 second. Huh? Yes. For an MOSFET source will be a lower voltage, because electrons have to flow from a lower voltage to the higher voltage. Right? So the generation of the carriers, the terminal that generates the carriers, or the terminal from which the carriers emanate, kind of, will be the same. But you are right. We'll come to that in MOSFET later on. Okay, so now let's assume that this is the device. And this is our 2-port. Okay. We'll not get into all the Y parameters, but let's assume we want to figure out what is the input Y parameters. Firstly, we cannot just leave it like this, we have to bias it, right? So, okay, so I haven't shown one terminal here, which needs to be shown. This diagram is incomplete. I haven't shown the body terminal, right? This terminal I haven't shown. By the way, body is never connected like this. Body is connected on the same side, but just for the ease of making a symbol or making a diagram, I have shown it like this. So the 4th terminal, that is the body terminal, is often shown like this. So this is B. Okay. And body naturally, in most cases, is connected to the power supply, because you don't want any forward bias PN junction. Was there a question? Okay. I haven't shown it here. Right now, I haven't shown. Right. This is only terminologies. Okay. So we'll get to how to connect which voltage to what. We'll basically get the definitions from wherever this picture, right? In the picture, we see the gate is grounded. So let's ground the gate. So let's say that for the time being, let's say gate is grounded. Yes. Okay, you are correct, right? I shouldn't have connected to a voltage source. Let's assume the gate is grounded. What about the source? In this case, it's 2 volt. Let's connect it to 2 volt to ground. Okay. What is body? Body is connected to the battery. Let's assume the battery is 2 volt. We are just establishing something, right? So let's say battery is also connected to 2 volt. Short it like this instead of dragging it all the way around. Okay. What about the drain? In this case, drain is connected to 1 volt. So let's connect the drain terminal to 1 volt. Okay. So let's continue, have a continuity of ground. Okay. So now we need to, if we say that this is the input port, if we say this is the input port and this is the output port, and I want to figure out what is Y11. So can you comment on what will be the Y11? Before we get into commenting on Y11, can you comment what will be the current I1 into this node? It will be 0, right? Because ultimately you see you have a capacitance here, right? One might argue that for if you have a sinusoidal input voltage, the capacitance will give way to some current. In fact, it does, but at this stage of the course, let's assume that the capacitance is small enough, right? So that it doesn't give way to any current. Okay, so we'll get into what happens when the capacitance becomes large enough to give some current, but that will be at the later half of the course. For the timing, let's assume that the capacitance is almost behaving like an open circuit in this case. Okay, so which means I1 is 0. If I1 is 0, and it is 0 continuously, right? For all values of V1, essentially I1 is 0. So what is the IV plot? V1, I1, what should it look like? It should be 0, absolute 0, right? So similarly, what will be the I1, V2 plot? This will also be absolute 0, right? So which means your Y11 is also 0, Y12 is also 0. Yes. You mean this horizontal line? Yeah. Yeah. Okay. I defined the terminal, right? So I just defined the terminal. I mean, because the device has been connected like this, we are just essentially saying that when you are defining a port, you have to define 2 terminals. One of the terminals is this. Where is the other terminal? I'm defining it like this. I mean, I am free to define it anywhere. I might as well have defined it as the ground. That's okay. Incrementally, there is no difference, right? It's the constant voltage source. Incrementally, this and this are sort of. Okay, so this is good, right? I mean, this in the sense that your the desirable characteristics of our Y parameters were the Y11 and Y12 should be 0, which looks like we are on the right. Okay, yes. Okay, so the reason so we defined, I probably didn't mark out the terminals, right? Okay, so if you recall with the analogy of the 2-port networks, so we would assume the way we were doing at that time was this was V1. Okay, so this was the input terminals and this was V2, right? But yeah, I should have marked it out. Thank you. I didn't understand. What do you mean by input voltage is -1? Okay, V1, absolute value of V1 is -1. That's okay, right? That's quiescent voltage. Okay, I'm not sure I understood your question. So let me rephrase what you are trying to ask. Are you asking this? What's the point of connecting this body to 2 volts? Right. Isn't that supposed to be like 2 volts? But and we see V1 turns out to be -1. Right. Okay. Probably now I get what you're trying to say. So what you are essentially, if I go back here, so I drew the exact structure that you see here in the bottom. Now I understand your question. Your question is, looks like this terminal here is at 1 volt, right? And this is 0. So this electric field need not be equivalent to a 2-volt battery, right? That's correct. So the electric field will be in this case for a 1-volt battery, right? But we didn't get into the device physics aspect of it. So when we put in those equations, you will see that this will take into account, it will not be the case. So this electric field will not be independent of whatever you connect at the drain and the source. It will be dependent on that, right? But still, we didn't put into the algebra of that governs the IV characteristics of the device. We are still in the intuitive domain, right? We are still trying to figure out how the charge flow or the carrier transport should look like. Okay, so as far as this Y11, the input parameters are concerned, we are good. But in order to figure out Y21, we have to go to the other terminal, right? We have to figure out what is the equations of the current flow. Without that, we cannot really figure out what is what will be the Y21 and what will be Y22. Okay, so which means that we have to put in some more effort to figure out what the charge profile looks like in a MOSFET. Okay, so let's do that. So now what I'll do, I will again rotate this. I have been rotating this between 90 degree and 0 degree, right? So let's rotate it around again. Let's rotate it around again and then try to figure out how it should look like. So I'm rotating it so that this is N type, and you have a distribution here. So let's call this the source. Let's call this the drain. Let's call this the gate. And you have a oxide or a dielectric in between. Okay, so this is P plus. This is P plus. For the time being, again, let us assume the biases have been set. However, the bias has been set. So let's assume for the time being, gate and source are connected together, because I am trying to figure out what will be the concentration of electrons in the channel or holes in the channel. So let's assume they are connected together. We'll put in some voltages later on. So let's say they are connected together and connected to VDD or connected to 2 volts or some supply. The drain and the bulk are also connected together. This is N plus. This is also connected together. And let's say this is connected to some voltage. Should I name it? Let's name it PSG. Right? So let's further assume that you have some voltage between the gate and the body. So the gate is also connected with respect to the source at a lower voltage, because ultimately what you want some voltage so that you want these electric fields to appear.
But D and S are the same.
Yes, for the time being, let's assume that D and S are connected at the same potential, right? We are again taking a step back because I want to understand what will be the profile of the charge in the channel, right? So the profile of the charge in the channel, even though it might look at this point, might be something quite scary, but it's not. Because ultimately, this is a parallel plate capacitor, right? You have a metal on top, and if the channel charge forms, you will have a sheet of holes underneath. So essentially, it's a parallel plate capacitor. In case of parallel plate capacitor, what is the only information that you need to figure out the channel charge? Is the capacitance, right? So if you know the capacitance of this dielectric, whatever is the dielectric, capacitance obviously depends on the thickness, the area, and so on. So if I know the capacitance, let's say I call this capacitance of the dielectric C ox total, you'll understand why I'm mentioning total. So let's say this is the total capacitance of the oxide or the dielectric. So the amount of the concentration of the charges here will be Q will be equal to Cox total times what? Times the voltage levels, which will be VSG in this case, right? Because you see this terminal, the difference between these two terminals is VSG, correct? So, but there is a catch, a slight amount of catch, because when I say this is the total, when I say that, when I write this charge equation in this form, I am taking into account the total charge in the channel. But we know intuitively that the total charge in the channel is a sum total of the mobile holes and the ionized dopants which are lying underneath. But the ionized dopants cannot move. They don't give us carrier transport. So we have to subtract the concentration of the ionized dopants in order to get the actual concentration of holes which can give us current, right? So something has to be subtracted, right? So now what is that something? In order to understand that something, we have to go deep into device physics. We don't want to do that. In fact, none of the circuit designers want to do that. So what we tend to do is to say that if from our intuition, we figure that it's not as if you connect a battery between the gate and the body or the gate and the source, and you are going to have hole concentration, or you're going to have mobile holes. You needed some voltage on top of some critical voltage, right, before the holes started to appear, because initial part was to deplete the charge, that region of any carriers. Do you recall that? So you had n-type, everywhere it was n, everywhere we had mobile electrons. We applied some voltage to drive the electrons away. So some voltage was needed to first free off that place. And then you apply some more voltage, and then the holes started to appear. So as long as we know that voltage beyond which the holes start to appear, then we are good. So that is a very important name for that. That name is called threshold voltage. Okay. So essentially, then if we know that beyond some threshold voltage or below some threshold voltage, there are no mobile charges, and above that threshold voltage, there are mobile charges. All we need to, the only conclusion that we can come out, the most important conclusion that arises is the fact that as if I subtract the threshold voltage from the applied voltage, I am getting the effective voltage that is giving me holes, right? Great. So essentially, then the hack becomes, you say Q mobile is Cox total times VSG minus some threshold voltage. Okay. So now this is not to be confused with Thevenin's voltage. Typically, we write capital T, capital H for Thevenin's. This is small t, small h for threshold voltage. Often you will see small t also. I mean, that also need not be confused with the thermal voltage, that is capital T. Okay.
What that C?
This Cx total, same sequence. Okay.
But Cx total is the capacitance of the capacitor only, or
yeah,
what does it mean by the total capacitance?
I'll tell you. That is the next thing in the agenda. So now, a natural question is why I'm saying that Cx total. I mean, Cox should mean the total capacitance. But there is again a nomenclature issue, and the nomenclature issue is the following. So often you will see later on, we are interested in the capacitance per unit area. The reason for that will become clear in the next class. But more often than not, we are always interested in the capacitance per unit area, which means that we'll have to define this Cox total in terms of capacitance per unit area times the area, right? So normally that's why we define this as Cox times the area of the cap times VSG minus threshold voltage. Now, if I have to figure out the area of the cap, I cannot figure out the area of the cap from this diagram, right? I have to look at kind of the top view, correct? So if I have to extend this, structure, and I have to redraw, I would redraw it like color have I used. I have to redraw it like this. So this becomes this essentially becomes one of the source terminals. This becomes the drain terminal. This becomes the gate terminal. And you see now the area of the capacitor becomes apparent, right? It's basically multiplication of this and this. And this region is called the length of the device, because the carriers have to flow through this entire length. And naturally, the other terminal is called, other dimension is called width or W. Okay. So your area cap becomes W times L. Now you will see that W and L are extremely important parameters. As it turns out, as circuit designers, we can control W and L. And we'll see that later, right? So given that we can control W and L, that is something we need to pay a lot of attention to. Okay, so your Q mobile becomes then Cox times WL times VSG. Now the Cox is again capacitance per unit area. Okay, not the total capacitance. Okay, any questions till now? Okay. So now that we have carrier concentration, we have charges, right? We have mobile charges in the channel. We can simply now say that forget about the gate, because the purpose of the gate is done. I've got the mobile holes concentration. Now, if I apply a voltage between the source and the drain, right? All I need to figure out what will be the current, right? So it's now back to a two-dimension, or rather one-dimension carrier transport, because all we are interested is to say that if I apply a battery voltage between the drain and the source, there will be a charge flow in this direction inside the channel. The holes will flow here. I need to figure out what will be that current. Okay, so that we can do now. So again, what is the conclusion? The conclusion is we have sufficient concentration of holes here. And we already have holes here. And we have now applied a battery between a region where you have only holes. Correct? So what do I need? I need to understand a very crude approximation is, all I need to understand is how much time does it take for this entire charge concentration to move from this point to this point. Right? I know the amount of charge there is in the channel. If I know the time it takes to move out of the channel, then I divide these two, I should be getting current. Right? So if we do that, so your current should be Q mobile divided by tau, where tau is essentially the transit time. Okay. So now, again, going back to rudimentary basics, if I know the velocity of the carriers inside the channel, then I should be able to get tau because I know the length, right? So tau should be length by velocity. Or in this case, we call it the drift velocity because carriers are drifting under the influence of electric field from one side to another. Okay. Okay, good. Now, what is drift velocity? If you recall, drift velocity is not infinite just because I've applied an electric field to a carrier, right? It's finite. and the proportionality constant, we call it as a mobility, right? So we call it mobility. So mu times E is the electric field. In this case, we call it mu P because we are talking about holes, right? P-type and P-type impurity. So, or P-type P variant of carriers. So we call it mu P times E. What is electric field? We know what the voltage applied between the two terminals are. We know the length. Electric field is voltage over length. So this becomes mu P times VSD, because the way I have connected, the source is at higher voltage. So VSD divided by L. So now put everything back. What do you get? Yeah, so tau becomes L by VSD by L square over VSD. So I put it back on I. So I get I to be equal to mu P also, right? Thank you. So mu P times L square times Q. Sorry, I made a mistake here. Did I write? This is right. Okay, let's put one by one, right? So Q mobile. Mu P will be in the denominator, right?
Q mobile.
Correct. Thank you. So mu P goes with VSD, right? Q mobile over L squared times mu P times VSD. And Q mobile was Cox times W times L times VSG minus some threshold voltage times mu P times VSD by L squared. One of these L's go. So you get an expression of I, which is mu P times Cox times W over L times VSG minus threshold voltage times VSD. This I is often also called ISD because just to indicate that the current is flowing from source to drain. If you leave it at I, it's also not a problem. Okay, so now you see that we have, I mean, from starting from very basics without much of algebra and without much knowledge about quantum mechanics or anything that relates to device physics, we have been able to arrive at some equation which will help us in analyzing the two-port Y parameters, right? Ultimately, we need an IV characteristics. The input. So this essentially is the output characteristics of the output current voltage characteristics. The input current voltage characteristics was quite simple. It was 0, right? Nothing was flowing in, but this is an output characteristics. Now, when we have an output characteristics, you can differentiate and figure out what will be Y21 and Y22. Okay, so we start off from here in the next class. Thank you.